let's review the types of things we can do with a set. If I have a set X, then I can check whether a point Y is an element of X or not. We could check whether a set A is a subset of X or not. We could apply the set operations of union, intersection, and complement to subsets of X. And if our set is finite, okay, we haven't defined that yet, but we know what it means intuitively, then we can count. If the set's not finite, then it's infinite. And again, we go with our intuition until we come up with a concrete definition. Now, for our next step, we want to talk about relations. So the idea here is we'll have two sets, say X and Y, and we want to link elements of X to elements of Y. Ultimately, this is going to lead to the familiar territory of functions. For here, I'm just going to assume that I'm linking elements from the set X back to the set X itself. And we'll call these relations binary relations. Now, before we get to that, we're going to need another set construction. So this is what we'll call a Cartesian product of two sets, X and Y. We write this like this. The elements of this set are going to be all ordered pairs, X, Y, where X is in X and Y is in Y. Now, for an example, let's take X equal to 1, 2, Y equal to 3, 4. For the Cartesian product, we're just going to take all ordered pairs. So I'll have 1, 3, 2, 3, 1, 4, and 2, 4. Now, if we want to compare elements, okay, we have to tell when 2 points are equal. So I'll have that the ordered pair AB equals CD if and only if A is equal to C and B is equal to D. So for instance, if we compare 1, 3 and 1, 4, they're not equal because 3 is not equal to 4. For us, we want to be able to take the Cartesian product of any finite number of sets. For instance, we take X and Y as before, Z equal to 1, 3. I could form the Cartesian triple product, X cross Y cross Z. That consists of all ordered triples, X, Y, Z, where X is in X, Y is in Y, Z is in Z. If we work this out, we get the following 8 elements. Now, to check our work, we could use the matching rule to see that we would expect 8 elements to come out. So we have 2 elements for X, 2 elements for Y, 2 elements for Z. If we multiply through, we get 8, as promised. Now, that gives the rule for the number of elements in X cross Y when X and Y are finite. So, number of elements in the product is just the number of elements in X times the number of elements in Y. Now, definition. A binary relation R on X is just going to be a subset of the Cartesian product of X with itself. For notation, if the ordered pair XY is in R, we'll write XRY. Now, we have many familiar binary relations, so for those, we won't need to make reference to this Cartesian product. For example, if we took X equal to the natural numbers, okay, 3 relations we use often, okay, strictly less than or equals, or equals. For instance, if I take, okay, the relation 1 strictly less than 2, we could write that as 1 R1, 2, or I could say that 1 comma 2 is an element of R1. If I want to say the relation doesn't hold, so for instance, I have 3 is not strictly less than 3, I would put a slash through the relation. So I have 3 slash R1, 3, which is the same as saying that 3 comma 3 is not an element of R1. Okay, for an example with the other relations, I could have 3 less than or equal to 3, so 3 R2, 3. 3 equals 3 just gives 3 R3, 3. In general, we can have situations like the following. suppose x is equal to 1, 2. We'll take the Cartesian product of x with itself, so I'll have 4 elements. Then we'll take any subset. So here I'll have R equal to the subset consisting of 1, 1 and 2, 1. Then I'll have 1R1, 2R1, 1/R2, and 2/R2. Next, we'll be interested in binary relations with special properties. So let's list a few of these. First, I'll say that R is reflexive if x are x always. So that just means that we have x comma x in R for all x and x. Then we have symmetric. This just says if x are y, then we also must have y are x. So if xy is in R, then we also have yx in R. For transitive, okay, this just says if x are y, y are z, then we must have x are z. So here effectively we're just collapsing the inside. For anti-symmetric, this says if y are x and x are y, we must have x is equal to y. Finally, anti-reflexive, this just says x/Rx always. So x comma x is never an element of R. Now, for examples, let's use our set equal to the natural numbers. Then we have less than or equals, equals, and strictly less than. For less than or equals, this is reflexive, anti-symmetric, and transitive. Okay, it's reflexive because we have x always less than or equal to x. For anti-symmetric, if x is less than or equal to y, y is less than or equal to x, then x is equal to y. Finally, for transitive, if x is less than or equal to y, y is less than or equal to z, then we must have that x is less than or equal to z. So for equals, we have reflexive, symmetric, and transitive. We'll say more about these three in a bit. And for strictly less than, we have transitive. Okay, it's vacuously anti-symmetric. Okay, we can never have the antecedent for anti-symmetric to happen. And we'll also have anti-reflexive. There are certain structures that repeat again and again in mathematics when we combine these special properties. First, we'll say that X is a partially ordered set or a poset, if and only if the relation R is reflexive, anti-symmetric, and transitive. For an example, we can consider X to be the natural numbers, R to be the relation less than or equal to. In this case, we could draw a picture as so. So the idea is going to be, as we are smaller and smaller, we get lower and lower on the graph. And then I draw a link whenever we have our relation holding. Okay, note I could put a link in from 1 to 3, but by the transitive property, I know that if I have 1 related to 2, 2 related to 3, then 1 is related to 3. So no need for that extra link. Another poset. Let's let X be the divisors of 24. Okay, so we have these integers here. Our relation is going to be divides. We have that this is also a poset. And again, we could set up a graph in the same manner as before. Okay, and this type of graph we call a Hasse diagram. So it looks like this. So we have 1 divides 2, 2 divides 4, so 1 divides 4, and so on. Another example, let X be any set. We'll form the power set of X. So that's a set consisting of all subsets of X. On that set, we'll put the relation of inclusion. So, for instance, if we take X to be 1, 2, 3, I could form the power set, which has 8 elements. Under inclusion, we'll get the following Hasse diagram. Now, for a special case of a poset, we have totally ordered sets. So a totally ordered set is going to have all the conditions of a poset, plus the condition that either X is related to Y or Y is related to X. Now, what does this extra condition do? So we'll see this in the following examples. So we'll use less than or equals. I'll let x be equal to the natural numbers, integers, rationals, reals, so on. The point is going to be that when we draw the Hasse diagram, okay, I can put it on its side, it's always going to be in a straight line. Now, final comments on posets. So what do we get from working with posets? First, we have a language for maximum and minimums, and for upper bounds and lower bounds. One advanced idea that we get out of this is called the Hausdorff maximal principle. So this says in a poset, every totally ordered subset is contained in a maximal totally ordered subset. Now, this isn't hard to believe when our poset's finite. So for example here, okay, if I wanted a totally ordered subset, I could just take the straight line going from the empty set to the set 2, 3. The Hausdorff maximum principle says that I could finish this off to a totally ordered set that runs all the way from the bottom to the top. Now, that's easy to believe when we have a finite number of elements. When we have an infinite number of elements, okay, this is going to be an equivalent statement to the axiom of choice, and it opens the door on some things that defy intuition. Now, another special class of relations are equivalence or congruence relations. So definition, we'll say a relation on a set X is an equivalence relation if and only if a relation R is reflexive, symmetric, and transitive. So the prototype for an equivalence relation is the relation of equals. So if I let X be any set, I can say X is related to Y if and only if X is equal to Y. So let's just check our three properties. So X is always equal to X. If X is equal to Y, then Y is equal to X. And if X is equal to Y and Y is equal to Z, then X is equal to Z. So this is an equivalence relation. Now, equivalence relations will come in many flavors besides just equality of elements. So for instance, if I let X be any set, I can let X be related to Y always, and then we'll have our three relations. Okay, you note as you go through each three, they're all true because anything goes here. For something a little bit less trivial, let's take our set to be the integers. I'll say X is related to Y if and only if X minus Y is even. This is going to be a special case of another equivalence relation, okay, another class. So here we'll have X, the integers. I'll fix some integer n greater than 1. And we'll say that X is related to Y if and only if X minus Y is some multiple of n. So here we're saying that X and Y are going to be related if they have the same remainder when they're divided by n. Now let's just check the three properties. So for reflexive, okay, if we take X minus X, we're going to have 0 times n, so that works. For symmetric, if I have X minus Y equal to K times n, then we'll have that Y minus X is equal to minus K times n. K is an integer, then so is minus K, so that works. Then for transitive, if we assume X minus Y is equal to Kn, Y minus Z is equal to Ln, okay, we can add those. Okay, so the middle Y goes away, giving me X minus Z is equal to K plus Ln. K plus L is an integer if K and L are integers. So this is going to be an equivalence relation also. Now, to see what an equivalence relation is really doing, we need another definition. We'll say the equivalence class of the element X in our set is given as the set of all Y in our set such that Y is related to X. Then I'll denote this E sub X. Now, let's run this definition through our examples. In our first example, where the relation was equality, E sub X is going to be the set of all Y in our set such that Y is equal to X. So there's only one element in this equivalence class, and that's going to be X itself. For our second example, okay, where the relation was y is always related to x, the equivalence class of x is just going to be all y and x. So that's our set x itself. Finally, if we take the example with the integers, okay, we fix our x. E sub x is going to be all y in the integers, such that y minus x is a multiple of n. Now, here, if I let that multiple be 0, we get x itself. Then I can start subtracting n from x or adding n to x. So here we're just going to get x plus or minus all multiples of n. In a special case when n is equal to 2, E0 is the even integers, E1 is the odd integers. Now you'll notice, okay, with each of our examples, if I take all the equivalence classes, okay, put them together, take their union, we get back our entire set. You'll also notice, if we take the intersection of any of these sets, okay, so for instance the intersection of the evens and the odds, we always get the empty set if they're not equal. This is going to point out what's happening with an equivalence relation. So the picture is going to look like this. If we have an equivalence relation, we're going to take our set x and we're going to chop it up into these equivalence classes. So we could think of an equivalence relation as a sorting mechanism. X is going to be related to y if and only if x and y share some quality. So x is related to x because x will share that same quality with itself. If x is related to y, okay, x and y have that same quality, then y and x have that same quality, and then you can just talk through transitivity in the same way. So if x and y have that same quality, y and z have that same quality, then so do x and z. Now, to make sense of this mathematically, I need another definition. Okay, definition of a partition. So if we have a set x, a partition of x is going to be a collection of subsets, E sub I. If I take the union of all the E sub I, we get back our set x. If I is not equal to j, then the intersection of E sub I and E sub j is the empty set. So these two sets will be disjoint. So the picture for that is exactly what we have here. Now, that's a theorem. Every equivalence relation, partitions our set x into equivalence classes. Conversely, every partition arises from some equivalence relation. So that means these two ideas are equivalent. For the proof, okay, for our first statement, I'll let x be a set. R will be an equivalence relation. We're going to show two things. First, if we take the union of the equivalence classes, we get back the entire set x. Then, if I take the intersection of any two classes, we get either that the two classes are equal or the intersection is the empty set. Now, for the first statement, we're going to show mutual inclusion. In one direction, it's clear because of the E's sub x, the equivalence classes are always subsets of x. If we take the union, that'll still be a subset of x. In the other direction, okay, I want to pick some x and x, show that it lives in the union. Now, the element x is always in the equivalence class for itself because we have the reflexive property. So that means x is going to be in its class, so it's going to be in the union of all the classes. That means little x is going to be an element in our set x. So we have our mutual inclusion and these sets are equal. Now, for the second statement, if the intersection is non-empty, then there's going to be some element in there called z. And for z to be in both of these sets, we'll have that z is in E sub x, z is in E sub y. And that just means z is related to x and z is related to y. By the symmetric property, we could flip this first one so that I have x related to z. Then by transitivity, I could take x related to z, z related to y, collapse to get x related to y. Now, that means x is in the equivalence class for y. we're going to do that trick one more time. So I want to show that the equivalence class for x lives entirely in the equivalence class for y. So if I pick a w in the equivalence class for x, w is related to x. We have x is related to y, so w is related to y by transitivity. That means w is in the equivalence class for y. So since the y is arbitrary, we have that e sub x is contained in e sub y. Using that same exact argument, we get the reverse inclusion. So these two equivalence classes are equal, and that shows our first statement. Now, there's one very useful consequence of that last proof. We have the relabeling rule. So if y is in the equivalence class for x, then the equivalence class for x is the same as the equivalence class for y. So if y shows up in here, I can just relabel this with the y. Now, let's show the converse. So I want to suppose I have a partition. How do I get an equivalence relation out of that? I'll assume our partition of x is given by the sets S sub I. The equivalence relation that we'll use, x is related to y if x and y belong to the same S sub I. Now, it's clear that this is reflexive and symmetric. Transitive, we're going to need to show some work. So, the problem is, we could wind up with a picture that looks like this. Here I have x related to y related to z, but x is not related to z. Because we have a partition, that's not a problem. If I have x related to y, that says that x and y are in some S sub I. Y is related to z. We have y and z in the same S sub j. If we take the intersection of these, we know that we have at least y in both of them. So if the intersection's not empty, then these two sets are equal. If they're equal, then that means that x and z are in the same S sub I, so they're related and we have transitive. So that means we have an equivalence relation coming from the partition. One last note, if I have different equivalence relations on a set, then we expect to have different partitions. So for instance, let's suppose our set is of 3 coins. I have a 1968 penny, a 1995 penny, and a 1968 nickel. First relation, R1, is if they have the same year. So in that case, I'll get the partition penny 68, nickel 68, union with penny 95. But let R2 be the same type. Then we'll have penny 68, penny 95, union with nickel 68. So we get 2 different partitions coming from 2 different relations.